which results from an unequal sharing of electrons between oppositely charged ions. Ionic bonds. As discussed earlier, the ionic bond is the electrostatic force of attraction, which results from an unequal sharing of electrons between oppositely charged ions. Many biological molecules are ionic at physiological pH 7.4. For example, proteins containing residues glutamic acid, aspartic acid, histidine, arginine, and lysine are charged at physiological pH. The acidic amino acid residues such as glutamic acid and aspartic acid, being negatively charged at pH 7.4, tend to interact with the basic amino acid residues such as histidine, arginine, and lysine. The positively charged ions will attract negatively charged groups, but at the same time, repel the positively charged ions. Similarly, the negatively charged ions will attract positively charged groups and repel the negatively charged ions. The extent of interaction depends on the local environment of the protein. If the salt concentration is higher in a system, the extent of interaction is weakened. A lower concentration of salt hardly affects the extent of interaction. Besides the physiological pH 7.4, the charges of the side chains of the amino acid residues at acidic and basic pHs are of utmost importance. The charges are the deciding factors for various proteins to function. Franz Hofmeister studied the effects of a series of cations and anions on the stability of secondary and tertiary structures of protein. The Hofmeister series, also called the Light-Tropic series, classified ions based on its effect on salting and salting out phenomena of protein. The order of cations and anions is given as F approximately equals SO4 and GT HPO4, 2 and GT CH3COO and GT Cl and GT NO3 and GT bridge and GT CLO3. The term hydrogen bond was first mentioned by Linus Pauling in 1935 to account for the residual entropy of ice. Hydrogen bond, abbreviated as H bond, is defined as an electrostatic force of attraction between an H atom, which is covalently bound to a more electronegative atom or group being H bond donor DN, and another electronegative atom being an H bond acceptor AC. Such a system is generally denoted as DNHAC, where the solid line denotes the covalent bond, and the dotted or dashed line denotes the hydrogen bond. The donor atoms are usually nitrogen N, oxygen O, or fluorine F. Hydrogen bond is much weaker as compared to the covalent bond. Both intermolecular and intramolecular H bonding occurs in living organisms. Intramolecular H bonding exists in the structure of protein and nucleic acid. The hydrogen bonding between water molecules is an essential intermolecular H bonding in a biological system. There exists an essential role of the H bond in protein chemistry. The secondary structure of a protein is formed by intermolecular H bonding NHO equals C between the amino acid residues. Hydrogen bonding is also responsible for the formation of tertiary and quaternary structures of protein. Hydrogen bonds also aid assistance in protein folding. Hydrogen bond carries a significant role in nucleic acid chemistry. The base pairs in DNA are formed by H bonds. There are 2 and 3 H bonds in the base pairs A equals T and G is defined as C, respectively. Hydrophobic forces. In a polar medium, the interaction between nonpolar molecules is known as hydrophobic forces. The word hydrophobic groups is derived from water-fearing groups. In an aqueous medium, the hydrophobic groups tend to maximize the hydrophilic area of contact and minimize the hydrophilic area of contact. Hydrophobic interaction is entropically driven. Due to hydrophobic interactions among nonpolar molecules, the surrounding polar molecules get free from the surface of the interaction, thereby increasing the entropy of the system. In protein chemistry, the hydrophobic amino acids such as alanine, olive, valine, gal, leucine, glue, isoleucine, phenylproline, prophenylalanine, methionine, met, and tryptophan TRP form the hydrophobic core during protein folding. Whereas the hydrophilic amino acids such as aspartic acid, S, glutamic acid, glue, arginine, art, lysine, wheat, etc., reside at the surface of the protein molecule, interacting with water molecules and forming hydrogen bonds. Van der Waals forces. Van der Waals force, also known as dispersion force and London force, has explained the weak interactions in gases, liquefied and solidified G gases, and NDLSOINM for organic liquids and solids. The forces are named after the Dutch physicist Diederik van der Waals, who postulated these intermolecular weak forces which play a role in real gases. Solids that have van der Waals forces as the primary force of interaction have lower melting points and are softer as compared to those solids which are held by stronger forces such as ionic, covalent, and metallic bonds. Van der Waals forces are the weak intermolecular interactions, approximately 1 kilocalorie mole -1, between permanent charges, dipoles, quadrupoles, or multipoles, which are within a ranging distance of less than 0.6 nanometers. There occurs attraction between molecules at a distance less than 0.6 nanometers. Repulsion occurs below 0.4 nanometers. They are not called as bonds because these forces are fluctuating induced dipole interactions and act in a very short range. They are non-directional. Van der Waals forces have 3 sources, which are described as follows. This force may arise from molecules that are electrically neutral. The force exists due to permanent electric dipoles. Fixed distortion in the molecule for distribution of electric charge. One side of the molecule is induced to be positive, and the opposite side is induced to be negative. The induced dipoles tend to align each other, resulting in a net attractive force called van der Waals force. This force may also arise from a permanent induced dipoles in molecules, which temporarily distorts the electron charge of other neighboring polar or nonpolar molecules, followed by induction of further polarization in the neighboring molecule. When no molecule present in a material or permanent dipoles. For example, in noble gas such as argon or inorganic liquids such as benzene, a weak force of attraction exists between the molecules, which accounts for condensing to the liquid state at sufficiently low temperatures. In the potential energy graph of the hydrogen H2 molecule, it is observed that when 2 atoms come close to each other, attraction occurs between them. The atoms attract each other to achieve the most stable state, where the radius r and the potential energy E in the potential energy curve of the bond length and bond strength of the molecule, respectively. Beyond this point, repulsion occurs between the atoms and energy increases as a result. The equation is as follows, where and B are attractive and repulsive force constants, respectively. All the interactions described here are weak. Here potential energy is a function of radius r. 612 ABB. R minus equals plus 16. Figure 1.53 the energy graph of hydrogen molecule. Potential energy graph of the hydrogen molecule showing attraction followed by repulsion of 2 atoms depending upon the radius. In protein folding, van der Waals interaction plays a major role in stabilizing the protein structure. During the hydrophobic collapse of a protein, the van der Waals interactions exist between the hydrophobic amino acid residues stabilizing the structure of the protein. Table 1.5. Type of bond covalent ionic hydrogen hydrophobic. Force. Van der Waals force. Energy. kcal mole -1, approximately 100 to 5, approximately 3 to 3, approximately. Strength strong weak weakest. Table 1.5 summary of chemical interactions in biological system. Bioenergetics and metabolic pathways are enzyme-assisted series of biological reactions that lead to anabolic reactions, which need energy, and catabolic reactions, which produce energy from a natural product within a cell tissue, as represented below. X for an anabolic reaction is the production of huge protein from amino acids and DNA from nucleic acids. The reaction course is significant to the life of the cell and requires energy offered by high-energy molecules like ATP, NADH, and NADPH. Catabolic reactions release energy stored in the bonds by degrading complex molecules into simpler ones and can store energy to synthesize ATP, which is the power to carry out all cellular reactions. Lipids also undergo catabolic reactions, thereby releasing energy and utilized for the synthesis of ATP. Enzymes act as a catalyst in catalyzing the chemical reactions of a metabolic pathway. The aerobic respiration metabolic pathways like glycolysis and Krebs cycle release different cellular molecules like ATP, and most of the metabolic reactions are non-spontaneous. X catabolic reactions fuels carbohydrates, fats. Catabolism. Carbon dioxide plus water plus useful energy. X anabolic reactions. Useful energy plus small molecules. Anabolism. Complex molecules. There is another metabolic pathway called the amphiphilic pathway, in which reaction pathways are either anabolic or catabolic. Figure 1.54 schematic representation of catabolism and anabolism reactions. Bioenergetics. Bioenergetics is defined as studying of energy transfer in living things during the biological reactions. Chemical bonds will break and reform with the exchange and transformation of energy in living cells. The formation of strong bonds and breaking of weaker bonds will release useful energy for work. The major 3 factors that establish biological, chemical reactions are free energy, enthalpy, and entropy. Thermodynamics. Thermodynamics deals with the studying of energy transfer, particularly the translation of energy from one form to another, and this obeys the first 2 laws of thermodynamics. It explains the pathways of coupling reactions and the transport of material in biological reactions. Laws of thermodynamics. In living organisms, the energy is directed by 2 fundamental concepts, i.e. chemical energy stored between atoms of a molecule and light energy absorbed by plant leaves. Laws of thermodynamics consist of 3 laws. First law of thermodynamics deals with conservation of energy, and the principle states that the total amount of energy can neither be created nor be destroyed, but it can change from one form into another form in the cosmos with any physicochemical modification. Therefore, the overall energy of the world or any other closed system is constant. Energy transforms either through heat energy by heating or cooling a substance or by physical work like movement. Hence, heat and work are both considered as equivalent forms of energy. The second law of thermodynamics defines that the entropy or randomness of disorder will continuously increase in a closed system with time. The entropy is represented by S and units of S equals J per mole, K. The equilibrium state in the reaction system has maximum entropy. Spontaneous reactions are those which take place without any external influence of energy and transform order the system to a disordered system. Change in entropy is indicated by increment S. System equals body, i.e., cell or organism and its surroundings. When a solid material is transformed into liquid or gaseous forms, the entropy of the surroundings rises. This is due to increased freedom for movement with change and transformations, as depicted in Figure 1.55. The entropy of the surroundings increases when a chemical reaction produces an increased number of molecules. Figure 1.55 Concept of entropy. Increase in entropy with a change of states from solid to liquid to gas. Standard mathematical form of second law. Delta S system plus delta S surroundings equals delta S universe, where delta S universe and GT, 0. Represents that the entropy of the system can decrease as long as there is an enhancement of equal or greater magnitude in the surrounding entropy of the system. Increment S equals S products S reactants. Plus increment S increased entropy, S products and GT, S reactants increment S decreased entropy, S products and LT, S reactants. Concept of free energy or Gibbs free energy. Free energy is described as the usable energy accessible to do work or energy present in a biochemical reaction that is accessible after accounting for entropy at constant temperature and pressure. Free energy is also called as Gibbs free energy and is designated as G. The change in energy is designated by the increment symbol, and hence change in free energy is represented by dG. When a biochemical reaction occurs with the liberation of free energy, is known as an exergonic reaction and represents a negative sign for delta G. Similarly, when a reaction proceeds by consuming free energy is known as an endergonic reaction, and the delta G is positive. The heat content of the reaction system is represented as enthalpy and deals with heat absorbed and emitted by system at constant pressure. Enthalpy is represented by H and change in enthalpy by delta H. When a biochemical reaction takes place with the release of heat is called an exothermic reaction, where the heat content of the product is less compared to the reactants, and delta H shows a negative sign. Similarly, when the reaction proceeds by using surrounding heat, it is called an endothermic reaction, and delta H shows a positive value. Entropy is disorder or randomness in a system, box 13 to 1. The units of delta G and delta H are joule per mole or calories per mole. Units of entropy are joules per mole, degree Kelvin, J per mole, K. The free energy, enthalpy and entropy is related by formula. G equals H, Ts. The biochemical reaction pathway and the degree to which a chemical reaction proceeds can be estimated by changes in three factors during reaction at constant pressure and temperature, i.e. changes in free energy, enthalpy and entropy. Delta G equals delta H T delta S. Where delta G equals change in free energy of the reaction system, delta H equals change in enthalpy of the system, T equals absolute temperature, and delta S equals change in entropy of the reaction system. When the entropy increases, delta S will have a positive sign, and when heat increases, delta H will have a negative sign with the release of heat from the system to its surroundings. These are favorable conditions to make a spontaneous reaction, where delta G is negative. Delta G equals G products, G reactants delta H equals H products, H reactants delta S equals S products. S reactants living organisms takes free energy in the form of nutrients from the surroundings or solar energy and returns equal energy as heat and entropy to the surrounding. Cells transfer free energy to ATP and energy-rich molecules, which offer energy for biological reactions at a constant temperature. Aerobic organisms take out energy from glucose, which obtains from the surrounding and releases CO2 and H2O as the end product to the surrounding with increased entropy, while the organism retains a steady state with no change in its internal order. The reaction system composition changes until equilibrium is reached, and at the equilibrium, the forward and reverse reaction rates are equal, and no additional changes take place in the system. Figure 1.56 graphs are representing positive, negative, and equilibrium states of delta G. When delta G is positive or in GT, 0, the reaction is non-spontaneous and is called endergonic. Energy is required to carry out the reaction. Delta G equals 0, the reaction is at equilibrium. Delta G of the forward reaction and backward reaction is equal in magnitude although opposite in sign. A. Minus 5 kilojoules. 5 kilojoules. Standard free energy. Cells are the isothermal system that functions at constant pressure and temperature. The energy that cells utilize for the biological reaction is free energy, G, which determines the path of the chemical reaction, equilibrium point and the amount of work cells can do at constant pressure and temperature. Standard free energy, abbreviated as delta G degree, is defined as the change in energy when reactants and products are at a concentration of 1 mole per liter at standard pressure and temperature 25 degrees Celsius. Unit of delta G degree is kcal, mole or kJ per mole. Delta G degree can also be defined as when reactants and products at standard conditions, i.e. 1 m concentration at 25 degrees Celsius, the energy driving the reaction system towards equilibrium is defined as delta G degree. In heterotrophic cells, the free energy is given by nutrient molecules, and in photosynthetic molecules, the free energy is given by solar radiation. Both heterotrophic and photosynthetic cells can convert this free energy into ATP and energy-rich molecules, which offer energy to biological reactions at a constant temperature. The above reaction occurs at standard pressure and temperature. However, the concentration of A, B, C, and D are not equivalent and does not have a 1 m concentration. In order to determine actual delta G under these non-standard concentrations as the reaction initiates from left side to right side, we enter the real actual concentration of A, B, C, and D in the equation. Delta G degree equals delta G degree products delta G degree reactants. When delta G degree is negative, the reaction takes place spontaneously under standard conditions, and the product possesses smaller free energy compared to reactants. When delta G degree is positive, the product possesses higher free energy compared to reactants, and the reaction takes place in the reverse direction under standard conditions. Delta G is 0 at equilibrium in biological reaction, where the reaction in either direction is not driven by any energy. 0 equals delta G degree plus RT lane kek, delta G degree equals RT lane kek, GRT kk. EQ lane, products. Reactants. C, D, B. Where R equals gas constant and T equals room temperature. The reaction spontaneity depends on delta G, not delta G degree. Delta G degree equals RT lane KEQ or delta G degree equals minus 2.303 RT log 10 KEQ or KEQ equals 10 delta G degree 2.303 RT. Phosphoryl group transfer. Phosphoryl group transfer reaction is a significant biologically important reaction for synthesizing energy-rich compounds like ATP, also known as energy currency. Phosphoryl transfer reaction is defined as the transfer of phosphoryl group PO3 from a phosphate anhydride or ester to a nucleophile. Phosphate monoester undergoes hydrolysis through nucleophilic attack by water is represented in the below reaction, finally producing inorganic phosphate, and this dephosphorylation reaction is catalyzed by phosphatases. Phosphate esters are omnipresent in the living world, for example, RNA and DNA are phosphodiesters. Phosphoric acid plays a significant role in nucleic acids by linking two nucleotides through an extremely steady bond and staying negatively charged at physiological pH. Phosphoryl group transfer happens from a phosphoryl group donor molecule designated R2 feet in the figure below to a phosphoryl group acceptor designated R1 foot. The figure below illustrates the transport of a single phosphate group from R2 to R1. X. Alcohol can be converted into organic monophosphate by accepting one phosphate group of ATP, as represented in the below reaction. One more example is the conversion of glucose to glucose 6-phosphate. Mechanistic possibilities of phosphoryl transfer reaction and dissociative mechanism involve removal or leaving of ester group first followed by nucleophile. In this example, it is water addition. In associative mechanism, nucleophile addition takes place in the first step, followed by leaving of ester group in the subsequent step representing an addition elimination process. And in concerted mechanism addition, of nucleophile and leaving of ester group takes place in the same step or single step. Figure 1.57 mechanistic possible steps of phosphoryl transfer. The phosphoryl group transfer reaction is a very important mechanism in DNA and RNA polymerization. The significant aspect of phosphoryl transfer in biological reactions is that the Lewis acid electron accepting magnesium ions enhance the electrophilicity of the phosphorus atom. Phosphoryl transfer catalyzing enzymes bind Mg2+ ions with non-bridging phosphoryl oxygens on the substrate in such a way that they can interact. Phosphoryl transfer reaction is one of the energy coupling reactions and is generally utilized in the transmission of intracellular information. ATP has a higher PO3 group transfer potential with a higher negative delta G degree value compared to glycerol 3-phosphate, indicating a strong ability to transfer its terminal PO3 group to water. The high PO3 transfer efficiency of ATP is contributed by the discrepancy in products and reactants free energies and also attributed to hydrolysis products ADP and PI and structures of ATP. Another three significant features are electrostatic repulsion, resonance stabilization and stabilization due to hydration. The hydrolysis products have greater resonance stabilization in comparison to ATP, contributing to higher phosphoryl transfer potential. Compound kcal -1 kJ -1 phosphoenol -1 14.8 -61.91 free viscous rate -11.8. Hydrolysis of ATP. Adenosine 5' triphosphate ATP, also known as energy currency, is a foremost source of free energy in living cells. The energy accumulated in ATP can be liberated through direct hydrolysis or by group transfer. Figure 1.58 molecular structure of ATP. Direct hydrolysis of ATP consists of nucleophilic attack by H2O at the gamma G phosphate position of ATP followed by cleavage of the G-butane hydride bond. ATP plus H2O right pointing arrow ADP plus PI, delta G degree equals -30.5 kilojoules per mole. Direct hydrolysis of ATP generates energy in the form of heat, which can be used to cycle proteins through different conformations, for instance, in muscle contraction. Group transfer reactions require the covalent transfer of part of the ATP molecule to a substrate, e.g. an enzyme active site, which successively makes consequent metabolic reactions using this substrate more thermodynamically favorable. Phosphate position in ATP. Group. Transferred. Phosphoryl transfer. ACO3. 2. Adenylyl transfer reaction is generally coupled with biological reactions, which has high positive standard free energy change attributed to the high negative standard free energy change of adenylyl reaction. For example, fatty acid adenylation, in which hexagonal adenylation of fatty acid and pyrophosphate catalyzed pyrophosphate hydrolysation is coupled to endergonic condensation of fatty acid and coenzyme A, yielding fatty acyl-CoA, AMP, and two inorganic phosphate molecules. Fatty acid plus CoA plus ATP right pointing arrow fatty acyl-CoA plus AMP plus PI increment G degree equals -34 kilojoules per mole. The hydrolytic cleavage in ATP cleaves terminal phosphone hydride bond among negatively charged free phosphate groups, resulting in the decrease of electrostatic repulsion in ATP and the resonance form stabilized generated PI. ADP2 is one of the hydrolysis products which ionizes fast, followed by liberating H+ into a medium of less concentration of H+ tilde operator 10 to 7m. Since ATP hydrolysis releases products with a concentration less than the concentration at equilibrium, hydrolysis in a cell is favored by mass action. Hydrolysis of ATP is an exergonic reaction with a standard free energy change of -30.5 kJ per mole at standard conditions but requires high activation energy for hydrolysis, which makes ATP stable at pH 7. Swift ATP hydrolysis happens when the reaction is catalyzed by an enzyme. The true free energy change of ATP hydrolysis in biological cells is extremely distinct due to the difference in cellular concentrations of ATP, ADP and PI and are considerably lower than 1m standard conditions. In most of the enzymatic reactions involving ATP is a phosphoryl group donor. The actual substrate is MgATP-2 because Mg2+ in the cytosol binds to ATP and ADP. The permanent standard free energy change is hence that for MgATP-2 hydrolysis. An Mg2+ complex moderately shields the negative charges and affect the conformation of the phosphate groups in ATP and ADP nucleotides. Figure 1.59 Mg2+ complex with ATP and ADP. High energy compounds. ATP is a high energy compound also known as energy currency with high energy bonds such as phosphone hydride bonds. High energy bonds are the one which releases high free energy when they are hydrolyzed, and the bond is represented by a squiggle tilde p. The complex metabolism processes are not feasible without the assistance of some energy-rich molecules. High energy compounds contribute significantly in transferring of inorganic hydride H ions. High energy bonds are the one which releases high free energy when they are hydrolyzed, and the bond is represented by a squiggle tilde p. The complex metabolism processes are not feasible without the assistance of some energy-rich molecules. High energy compounds contribute significantly in the complex metabolism processes are not feasible without the assistance. The complex metabolism processes are not feasible without the assistance of some energy-rich molecules. High energy compounds contribute significantly in transferring of inorganic hydride H ions or phosphate groups pi. ATP. ATP has high energy phosphoric anhydride bonds ascribed to electrostatic repulsion generated by positively charged phosphates and negatively charged oxygen which stabilizes ADP and PI products through the breaking of these bonds. The products of ATP are stably attributed to resonance structures of products along with the existence of high entropy, and disorders favored over orders for the second law of thermodynamics. 1 mole of reactants has higher energy compared to 2 moles of products. ADP. ADP adenosine diphosphate has the same structure as ATP with one less phosphate group and contains high energy bonds situated between each phosphate group, and the reasons are the same as ATP. NAD+. Nicotinamide adenine dinucleotide oxidized form NAD+ is an important electron acceptor in catabolic reactions and is strong sufficient to oxidize alcohol to cardinal groups. NAD+ is a significant molecule in various metabolic reactions like the TCA cycle, beta oxidation and glycolysis, and these reactions never happen in the absence of NAD+. Fat and other electron acceptors can only oxidize saturated carbon chains from alkanes to alkenes. NADH. Reduced form of NAD+ is NADH, where NAD+ has received electrons in the form of hydride ions. NADH plays an important role in oxidative phosphorylation and also pyruvate by donating electrons to etc. NADP+. NADP+, nicotinamide adenine dinucleotide phosphate, oxidized form, is the oxidized form of NADPH and donates an electron to the anabolic reactions. NADPH. NADPH is a reduced form of NADP+. Energy-rich compounds are the molecules that produce free energy which is equivalent to or superior to that of ATP. Increment G degree equals -7.3 kilocalories per mole on hydrolysis. Low energy compounds are the ones that yield energy less than -7.3 kilocalories per mole. Since high energy compounds are always associated with the phosphate groups, except acetyl-CoA, they are also known as energy phosphates. These are primarily divided into 5 groups. 1. Pyrophosphates consist of acid and hydride bonds formed by the condensation of acid groups, mainly phosphoric acid or their derivatives. X. ATP has 2 high energy diphosphate bonds with phosphone hydride bonds. 2. Enol phosphates. The bond present here is the enol phosphate bond, which is formed when a phosphate group attaches to a hydroxyl group which is bonded to a carbon atom having a double bond. X. Phosphoenol pyruvate. 3. Acyl phosphates. Reaction between carboxylic acid and phosphate group forms high energy bond. X. 1. 3 bisphosphoglycerate. 4. Thiol phosphates. It has high energy thioester bond established by the reaction between thiol and carboxylic acid. X. Acetyl-CoA. 5. Guanidinophosphates. The bond is known as guanidine phosphate bonds and is formed by the bonding between the phosphate group and the guanidine group. X. Phosphocreatine. Class bond. Pyrophosphate CPP. Acyl phosphate SO. CO tilde P. Enol phosphate CH. CO tilde P. Thiol esters thioesters C. Pipe. CO tilde S. Guanido. Phosphates I. NP. Compound. Other energy-rich compounds are phosphocreatine, AMP, PPI, glucose 1-phosphate, fructose 6-phosphate, and glucose 6-phosphate. The electron transport chain and oxidative phosphorylation. Oxidative phosphorylation represents the climax of energy-yielding metabolism in both aerobic prokaryotes and eukaryotes. Oxidation of various fuel molecules such as carbohydrates, lipids, and amino acids culminates at this final stage of cellular respiration, in which the oxidation energy drives the synthesis of high-energy molecules, ATP. Unlike O2-dependent oxidative phosphorylation, substrate-level phosphorylation occurs without oxygen, in which the phospho group is directly transferred from the phosphorylated substrate to ATP to form ATP. On the other hand, in the case of photophosphorylation, which occurs in photosynthetic organisms such as plants, solar radiation is captured and harnessed into making ATP. However, photophosphorylation is absent in animals and non-photosynthetic organisms. However, there are several similarities between oxidative phosphorylation and photophosphorylation. One, both processes require a flow of electrons via a chain of membrane-bound protein complexes, and two, the free energy made available owing to this downhill electron flow is coupled to uphill transport of protons across the membrane, creating proton concentration differences or electrochemical gradients, and three, finally, this concentrated protons move down its concentration gradient through specific proton channels, resulting into ATP synthesis. The electron transport chain, etc. An overview. A serial arrangement of four protein complexes of etc. with progressively increasing reduction potential helps oxidize NADH and FADH2, and free energy liberated so is used in a manner that leads to the synthesis of ATP. Electrons extracted from NADH and FADH2 by complex I and 2, respectively, are carried to complex 3 by coenzyme Q, copper-ubiquinone, and then to complex IB by the mobile peripheral membrane protein called cytochrome membrane protein called cytochrome circa. There, the O2 molecule eventually accepts electrons from cytochrome C and gets reduced to water. There are several inhibitors used in the study of the pathway of electron transfer which help to unveil the entire mechanism. Oxygen electrodes were used to measure the rate of O2 consumption. The underlying principle is that the inhibitors capable of inhibiting electron transport would decrease the rate of O2 consumption, which is measured by the oxygen electrode. Amongst the most useful inhibitors are rotenone, an insecticide amytal, a barbiturate antimycin, an antibiotic, and cyanide. The following experiments illustrated the order of arrangement of protein complexes in the electron transport chain. First, a buffer containing excess ATP and pi is placed in a reaction chamber of an oxygen electrode, and then specific reagents were added, and the O2 level was measured. 1. B-hydroxybutyrate and mitochondria are added in the oxygen electrode containing vessels. B-hydroxybutyrate is oxidized into acetoacetate with simultaneous reduction of NAD plus to NADH. The NADH then transfers an electron to ETS, eventually reducing O2 into H2O. Therefore, the level of O2 decreases, which is monitored by the oxygen electrode. Diagram shows the effects of various inhibitors and substrates on the level of O2, which is monitored by an oxygen electrode. The numbering in the figure is explained in text. 2. Following the addition of rotenone or amytal, oxidation of B-hydroxybutyrate stops, as the O2 level stops decreasing, but the only thing which can be concluded at this stage is that electron transfer is inhibited. 3. Addition of succinate in the vessel, which undergoes fad link oxidation, causes O2 to resume its decrease. This shows that electrons from FADH2 are still able to reduce O2 even in the presence of rotenone or amytal. Therefore, the entry of electrons from FADH2 must be after the rotenone block step in the electron transport chain. 4. Next, the addition of antimycin inhibits electron transport from FADH2, indicating that it must be able to create electron transfer blockage down the complex accepting electron from FADH2 in the electron transport chain. 5. Besides, NADH and FADH2 as physiological electron donors to the electron transport chain, there is a non-physiological reducing agent, such as TMPD tetramethyl PP-henylamine, which can directly transfer the electron to cytochrome circa. Therefore, the addition of TMPD to antimycin inhibited reaction causes resumption in O2 consumption. This indicates that there is a third point at which the electron can enter either from the previous step or directly the electron transport chain. 6. Addition of cyanide completely inhibits the oxidation of all 3 electron donors. Discussed above. This conclusively indicates that CN blocks after the third point of entry of electron in the electron transport chain. Isolation of components of electron transport chain complexes. Treatment of mitochondria by detergents such as digitonin removes the outer mitochondrial membrane. Thereafter, the mitochondria with the inner membrane are fragmented by osmotic rupture. These fragments, so obtained, are gently dissolved in a second detergent so as to obtain inner membrane protein complexes. These soluble protein complexes are resolved by ion exchange chromatography into different complexes, complex I, 2, 3, and IV. Besides, there is a fifth complex called ATP synthase, complexes I through IV. Catalysis the electron transfer from NADH and FADH2 to molecular O2. In vitro, isolated ATP synthase has ATPase. Activity ATP hydrolyzing, not ATP synthesizing activity. Figure 1.60 effects of inhibitors on electron transport. Figure 1.61 separation of functional complexes of the electron transport chain. Functional complexes I through the ATP synthase can be isolated by solubilizing the inner membrane of mitochondria followed by employing ion exchange chromatography. B components of the electron transport chain. There are 4 complexes in a set of electron transport chains. Each complex contains multiple proteins that remain associated with a variety of functional redox centers with progressively increasing reduction potential. Figure 1.62 the mitochondrial electron transport chain. The 4 complexes, numbered by IV, are shown embedded in the inner mitochondrial membrane. Complex I and 2 independently accepts electrons from NADH and FADH2, respectively, and then transfer it to coke, which passes the electrons to complex 3. Further, cytochrome C mediates the transfer of electrons from complex 3 to complex IB. Eventually, the O2 accepts electrons and get reduced in H2O. Let us look at the structural and functional aspects of each complexes and their associated redox center in greater detail. Complex I, NADH dehydrogenase or NADH copoxyreductase. It is probably the largest complex of inner mitochondrial membrane, composed of around 45 different polypeptide chains, 1 molecule of FMN flavonoid mononucleotide, a redox active prosthetic group, and at least 6 iron sulfur centers that participate in the electron transfer process. In mammals, around 7 of its 45 polypeptides, which are the most hydrophobic ones and form the core of complex I, are encoded by mitochondrial genes. The remaining polypeptides are encoded by nuclear genes. 1. Coenzymes of complex I. There are 2 coenzymes, namely FMN and coke, which work in association with complex. Both coenzymes can adopt 3 oxidation state and can accept and donate either 1 or 2 electrons. In contrast, the cytochromes of complex 3, to which reduce coke 2 transfers its electron, are only capable of 1 electron reduction. The hydrophobic tail of coke helps it remains anchored in the inner membrane lipid bilayer. In mammals, this hydrophobic tail consists of 10C5 isoprenoid units, and hence the coenzyme is also designated as Q10. In bacteria and plants, the function equivalent to coke is performed by related compounds called menaquinone and plastoquinone, respectively. Both FMN and coke, following acceptance of 1 electron, become semiquinone radical. Thereafter, accept 1 more electron and convert it into hydroquinone form, fully reduced form. 2. Iron sulfur clusters constitute functional redox centers. Helmut Beinert is credited to have discovered iron sulfur proteins. Iron sulfur clusters are commonly found in iron sulfur proteins as prosthetic groups. Unlike cytochrome, in which iron is present in heme, in iron sulfur protein, Fe is present in association with inorganic sulfur atoms or with sulfur atoms of C-wise residues in proteins or both. Complex 2. Succinate dehydrogenase. As stated earlier, complex 2 is only capable of injecting electrons from succinate to coke via FADH2, because the standard redox potential difference for electron transfer from succinate to coke is not enough to provide the free energy necessary for ATP synthesis by pumping protons from matrix to intermembrane space. Apart from complex I and 2, there are 2 other enzymes that cause the reduction of mitochondrial inner membrane coke into coke 2 and thereby power oxidative phosphorylation in mitochondria. For example, glycerol 3-phosphate dehydrogenase of the glycerol shell and ETF, electron transfer flavoprotein, ubiquinone oxidoreductase, which is involved in fatty acid oxidation. Figure 1.63. Figure 1.63 cathode electrons from NADH, succinate, fatty acyl-CoA, and glycerol 3-phosphate converse of ubiquinone. Electrons from NADH pass through FMN to a series of iron sulfur proteins in complex I and eventually to coke. Similarly, succinate passes electrons to a flavoprotein and then to Fe centers of complex 2 and finally to coke. Glycerol 3-phosphate dehydrogenase passes electrons from glycerol 3-phosphate to a flavoprotein located on the outer face of the inner mitochondrial membrane, and then electrons move to coke. Acyl-CoA dehydrogenase passes electrons to ETF and then to coke. 1. Cytochromes are heme proteins that transfer electrons. David Kalin, in 1925, elucidated the function of cytochromes, which are found in all organisms except a few types of obligate anaerobes. Cytochromes are proteins with the iron-containing heme prosthetic group. The heme prosthetic groups are redox active centers whose fate atom reversibly alternate between Fe2 and Fe3 oxidation states during electron transfer. Cytochromes have a characteristic absorption spectrum in visible light. There are three classes of mitochondrial cytochromes, designated A, B, and C, which can be distinguished on the basis of their characteristic absorption spectra. The heme cofactors of M B cytochromes are non-covalently associated with their respective protein, whereas heme C-type cytochromes are covalently attached through C-wise residue. The standard reduction potential of the heme iron atom of a cytochrome depends on its interaction with protein side chains, and is hence different for different cytochromes. Generally, cytochrome and B are integral intermembrane proteins of mitochondria, whereas cytochrome C is a soluble protein that associates via electrostatic interactions with the outer surface of the inner membrane of mitochondria. Each type of cytochromes in its reduced state, Fe2, has three absorption bands, designated as A, B, and G bands. 2. Complex 2 contains a linear chain of redox factors. Several empirical X-ray crystallography studies have shown that substrate and coke binding sites are connected by an almost linear chain of redox centers in the order such as Fab right pointing arrow 2 Fe2 S right pointing arrow 4 Fe4 S right pointing arrow 3 Fe4 S right pointing arrow coke. Electrons removed from succinate follow the above mentioned order and eventually reduce coke to coke 2. The heme B of complex 2 seems to be misaligned and not in the direct path of electron transfer from Fab to coke. It may help reduce the frequency with which electrons deviate from the system and produce harmful chemical species such as reactive oxygen species, rose superoxide. O2. Complex 3. Coenzyme Q cytochrome C reductase, also known as cytochrome B C1 complex or ubiquinone. Cytochrome C oxidoreductase transfers electrons from coke to the cytochrome C with vectorial transport of protons from the matrix to intermembrane space. This complex consists of 11 different types of polypeptides precisely folded in the quaternary structure. A typical cytochrome B C1 complex contains three components, namely cytochrome B that binds both BH and Bl hems, cytochrome C1 which contains a single C-type heme, and a Arisa iron sulfur protein with a 2Fe2S center. Of 11 different polypeptides, only cytochrome C is encoded by a mitochondrial gene, and the remaining 10 polypeptides are encoded by nuclear genes. Generally, the transfer of electrons occurs from reduced coenzyme to 2Fe2S to cytochrome C1 and eventually to cytochrome circa. Reduced cytochrome C mediates the passage of electrons from complex 3 to complex IB. Based on structural and biochemical studies of redox reactions, a rational model has been proposed to explain the passage of electrons with the concomitant translocation of protons through the complex 3. This is called its Q cycle. The Q cycle involves coke 2, which undergoes a 2-cycle reoxidation via stable semiquinone Q, intermediate. During the Q cycle, one molecule of QH2 carrying 2 electrons sequentially reduces 2 molecules of cytochrome C, as it can accept only 1 electron at a time, with concomitant translocation of 4 protons 4H+. There are 2 independent binding sites for Q, designated as Co and Chi. The Co site, located between the iron sulfur cluster and heme Bl close to intermembrane space, binds QH2, whereas the Chi site, located between heme BH in close proximity to the matrix, binds both Q and QH2. For every pair of QH2 that enters the Q cycle, 1 QH2 is regenerated while 4 protons 4H+ are translocated from the matrix to the intermembrane space of mitochondria. Note, the antifungal agents mixotriazole and sigma-tolin act by blocking electron flow from QH2 to 2Fe2S into heme Bl. Cytochrome C is a small peripheral membrane heme protein, belongs to the cytochrome C family protein, and is found loosely associated with the outer surface of the inner membrane of mitochondria. It shuttles and alternatively binds to cytochrome C1 of complex 3 into the cytochrome C oxidase of complex IB and therefore transfers electrons from former to later complex. Complex IB, cytochrome C oxidase. This complex has 13 different proteins and mediates the transfer of electrons from cytochrome C to molecular oxygen and thereby reducing O2 to H2O. The bacterial complex IB contains only 3 or 4 subunits. There are 3 crucial subunits among 13 polypeptides, which play an important role in the functioning of complex IB. The subunit 2 contains 2 Co ions complex with the SH group of C-wise residues and resembles an iron sulfur cluster 2Fe2S. Subunit I contains 2 heme groups designated Na3 and 1 copper ion designated as hub. The order of electron transfer through complex IB is cytochrome C right pointing arrow Cu right pointing arrow heme right pointing arrow heme A3 Cu center right pointing arrow O2. The oxygen binds to heme A3 and is first reduced to its peroxy derivative O2 by 2 electrons from the Fe center. Further delivery of 2 more electrons converts O2 to 2 molecules of H2O following acceptance of 4H+ from the matrix. The summary of the flow of electrons and protons is shown together. Figure 1.64 combinatorial representation of complex I2, 3 and IB of electron transport chain. Up shows important redox active centers located in the 4 complexes which actually participate in electron transfer by undergoing oxidation and reduction. B shows order and location of 4 protein complexes with progressive standard reduction potential. Chemiosmotic theory. This theory, proposed by Peter Mitchell, states that free energy liberated during electron transfer through electron transport chain is harnessed in a manner that results in translocation of protons from matrix to intermembrane space, forming electrochemical gradient proton motive force in the form of difference in proton concentration and separation of charges across the intermembrane, which, in turn, drives the ATP synthesis. Protons flow passively back to the matrix through a proton pore associated with ATP synthase. Several important observations can be explained based on chemiosmotic theory such as 1. The inner mitochondrial membrane is impermeable to ions including K+, Cl, H+, O whose free diffusion would dissipate electrochemical gradient created by electron transfer translocation of H+ from matrix to intermembrane space. 2. Mitochondria with intact, the impermeable inner membrane can perform oxidative phosphorylation. 3. All those chemical compounds that increase the permeability of the inner mitochondrial membrane for protons, thereby dissipating electrochemical gradient, inhibit ATP synthesis without affecting electron transfer from NADH or FADH2 to molecular oxygen via electron transport chain. It means that the presence of such compounds uncouples oxidative phosphorylation from electron transport. Conversely, increasing the acidity in the intermembrane space or outside mitochondrial cytosol stimulates ATP synthesis. Figure 1.65 chemiosmotic model. This model entails that electrons from NADH, Fod2 or any other oxidizable substrates, while moving through a chain of complexes in the inner membrane, drives the translocation of protons from matrix to intermembrane space, producing an electrochemical gradient referred to as proton motive force. Since the inner membrane is quite impermeable to protons, hence H+ may move back only through a specialized channel. The passive backward movement of protons, i.e., from intermembrane space to matrix, is driven by proton motive force, which is translated into ATP synthesis by ATP synthase complex. Chemiosmotic theory explains the intricate relationship among electron transfer, electrochemical gradient formation and ATP synthesis. Oxidative ATP synthesis in mitochondria is dependent on electron transfer through an electron transport chain consisting of multiple